Hi. In the previous session, we had discussed about sequences and their limits, their convergence, divergence, and everything. We will be carrying over all those concepts to the discussion of infinite series in this session. Okay. So before we discuss infinite series, let us understand what do you mean by finite series. So suppose we are adding a finite number of terms. For example, 1 plus 2 plus 3. Okay. When you add up, you will get a value. This is called the sum of the sum of this series. It is called 6. Okay, so this is a finite series. Okay, so when you add up the terms, so these are called terms. When you add up the terms of the finite series, you will be getting a sum. Okay, and you know that when you add up the terms of a finite series, it will always be finite and it will always be fixed. Okay, so these are some familiar things which we already know from practice. Now we will now discuss the concept of adding an infinite number of terms. So such type of expressions are called infinite series. So an infinite series is basically summation of an infinite number of terms. Okay, so usually we will write it using the symbol u1 plus u2 plus etc plus uk plus etc plus etc. Okay, so basically you are having an infinite number of terms here. Okay, so these ui's are called terms of the series, and when you add up, if you are getting a finite fixed value, we will call it as sum of the series. Okay, so this is the basic idea which you are going to carry over from the finite series. But the problem with infinite series is that always you won't get a finite fixed term as sum. Okay, so basically infinite series are not well behaved like the finite term series. They are very much complicated. Okay, so you suppose if you are randomly adding up some series, you won't be getting a finite value, you won't be getting even a fixed value. Sometimes you may get finite fixed value, sometimes you will be getting infinite value, sometimes you will be not be getting fixed value itself. I'll give you the examples also. So because of that, the discussion of infinite series is much more complicated, so you have to be very careful, because the familiar properties as in the case of finite series will not be obeyed in the case of infinite series. So you have to be very careful here. So we'll discuss this in detail now. So why are we studying this? As I told you earlier in the previous sessions itself, we are going to approximate functions using infinite series, and if you are using an infinite series which is bad, then it is not, there is no use of using that series, because if you are not getting a finite fixed sum as thus a sum of the series, it cannot be used for approximating anything. Okay, so if you are not getting a fixed sum, it cannot be used for approximating any type of function. So basically, when you are going to use infinite series in applications, you have to use the good series. So here we are going to identify the good series. So what are the good series? A good series is a series when you add up, you should get a finite fixed term. So when you add up that good series, you should get a finite fixed value as the sum. Okay, so only such series will be considered as good series, and those series are used in our applications. Okay, now let us see some examples of which types of series are good and which types of series are not good. Okay, for example, if I look at this series here, 1 plus 2 plus 3 plus 4 plus etc. Okay, so this series is actually what can be the sum of the series. If you just observe the series, you can see that it is going on increasing as the terms are increasing. Okay, so it will go on increasing as you bring in more terms. So this actually adds up to infinity. So the sum of the series is actually infinite. So this series is not a good series. And if you look at this series here, 1 minus 1 plus 1 minus 1 plus 1 minus 1, we have already seen the series before itself. Okay, so you know that you can either obtain the value as 0 or the value as 1 according to the way in which you add. Okay, suppose if I am adding just the first two terms, then the third and fourth terms etc, you will be getting the value as 0. Or if I am taking the first term and then you are adding up the second and third term, like this, if you are adding like this, you will be getting the value as 1. So depending upon the order of your adding, your values will be different. Okay, and suppose if I am taking this series, it is 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2. Okay, if you observe it closely, you can see this is a familiar geometric series. We'll discuss about geometric series in short time, but you already have studied this geometric series in your lower classes, so you know that the sum of an infinite geometric series is a by 1 minus r, provided modulus of r is less than 1. You have studied this before. So if you assume that you know this result, then the value of the series would simply be, here a is actually 1, the common ratio is 1 by 2, so the value will simply be 2. So I have given you 3 examples in which one example you had the sum as an infinite number. In one example you had a sum as not fixed. Here you have a sum as a finite and fixed. So this is a good series which will be used for application. So these two series will not be used. You should be able to identify which series are good and which series are not good. Okay. So before we discuss this concept more concretely, let us make some few observations. Suppose I want the sum of a series to be finite and fixed. Suppose I want the sum of the series to be finite and fixed. Okay, so what can you say? So suppose if I'm adding up u1 plus u2 plus u3 plus etc. Suppose my value is u1000. Okay, so if I add again, suppose if I add again, if I'm adding u1 plus u2 plus u3 plus etc. plus u1000 plus again u1000, and when I'm adding everything, should there be a significant difference between these two? Should there be a significant difference between these two? Okay, so if there is a significant difference between these two terms, what will happen? These two expressions, what will happen? It means that when you are adding up newer and newer terms, your sum is going on increasing indefinitely. Okay, so that means that you won't be getting a fixed value, or you won't be getting a finite value, because it is going on changing. It is going to change, right? For example, suppose I add up up to u1000. I added and I got the values maybe 2021. Suppose I got the value as 2021, and now if I'm adding up these two and I'm getting the value as maybe 2091. Okay, can you say that whether this series has a finite or fixed sum? Okay, you cannot say it clearly, but just think like this, because just by adding a single term itself you have got a variation of about 70 points here. Okay, so now if you are adding the next term, again you may get a bigger variation there. So that means if you go on adding up everything, you won't be getting a fixed value, or you won't be getting a finite value. It is going on increasing. Okay, so that was the case in these examples. So here you can see that when I add up 4, my sum got increased. Again if I add 5, again my sum got increased, etc. It is going up. Okay, but in this case, if you look at this one, you can see that if I add up here 1 plus 1 by 2 etc. Suppose I am adding 1 by 2 raised to 100 here. Okay, so this I'll get a value somewhere here. Plus again if I am adding the next term as 1 by 2 raised to 101, will that make a much difference? Okay, the contribution of this new term would actually be very significantly small. Okay, because this value is very, you can see that the value is very negligible. If it is 1 by 2 raised to 101, it is 2 power 101, its value will be very huge. But I am taking 1 by 2 power 101, so that means overall the contribution of newer terms should be very small. Okay, that means it will not affect the overall sum. So that is one common property of these series having fixed finite sums. Okay, for series have an infinite sums, what happens is that the terms contribution would be bigger. That is where the series is going on increasing. But for those series which have a fixed sum, the contribution of a kth term, when k is very big, it will actually be negligible, so that overall when you add up everything, you will be getting a fixed value. Okay, that is one simple observation I am trying to make here. Okay, so this is an idea of a series which has a finite fixed sum. Okay, this is the idea of a series which has a finite fixed sum. Okay, we'll make it more rigorous, but try to understand this concept here. It's very simple. Okay, because if the addition of this kth term brings a bigger change, you can't expect the series to be finite. Okay, you cannot expect the sum of the series to be finite. Okay, if the addition of a kth term increases the value of the sum to a bigger value, you cannot expect the series to have a finite or fixed sum there. Okay, it will go on changing. Okay, so that's the idea here. So how will you now define the sum of a series now? So we are going to say that a series, just like a sequence, sequence is convergent if its sum is finite or fixed. Okay, a series is said to be convergent if its sum is finite and fixed. This is the basic idea. Okay, otherwise we will say that the series is divergent. For example, this series, this is actually a convergent series. This is not a convergent series. This is not convergent series. Both these series are divergent series. Sometimes they also call the series as oscillatory series, but still I'll call it as divergent series. So when is a series said to be convergent? When its sum is fixed and finite. Okay, so as I told you, for a convergent series, the contribution of kth term, when k is large, should actually be negligible. Okay, otherwise the sum would be changing. Okay, so sum cannot be stay fixed or sum cannot be finite. So the contribution of kth term when k is very big should be negligible. Only then you can say that the series is convergent. Okay, now we will try to define this in more rigorous terms. Okay, so all these are just for your understanding, only for it is required. It's not required for examination, just for understanding. I'm going to introduce the concepts here. It's very simple. So I am going to define convergence or sum of a series by in terms of a sequences. Okay, how will you define the sum of a series in terms of sequences? Okay, suppose you are considering this series. I am going to define a new sequence. Okay, so let my sequence be S1 is equal to U1. Okay, and let my sequence S2, the second term of the sequence S2 be U1 plus U2. Okay, so for S1 I took just first term, for S2 I took both the terms, for S3 I am going to take U1 plus U2 plus U3. Okay, I hope you understand the sequence now. So what is the sequence? SK. So what is SK now? SK is nothing but U1 plus U2 plus etc. plus UK. Okay, now you can say that this series is called the sequence of partial sums. This series is called the sequence of partial sums. Okay, so this series is called the sequence of partial sums of the series because you are only adding a part of the series. Okay, that's why it's called sequence of partial sums. Now can you can you find a correlation between the convergence of a series and these partial sums? Convergence of a series and these partial sums. Okay, a series is convergent if its sum is fixed and finite. Okay, so as I told you, its sum is fixed and finite, or it means as you go on, see, look at these sequences. If you look at the terms of the sequence S1, S2, S3, etc., what should happen? This entire sum should be fixed and finite. So what will happen to here? So this means you have to see, when you look at this sequence here, this is actually part of the series only. So as this k goes on increasing, what should you get? These terms should be approaching a fixed value, okay, which is the sum of the series. Okay, so if this series is convergent, these SKs should be approaching the sum of the series, because these SKs are actually the series only you are taking the k terms only. So as k goes on increasing, this SKs should approach the sum of the series, or I will say that limit k tends to infinity sk. When you take limit k tends to infinity sk, you will be getting the sum of the series. So it should be s, which is finite and fixed. Okay, so this is how you define the sum of a series. So how is the sum of a series defined? The sum of a series is defined in terms of partial sums, limit of the sequence of partial sums. So already you know limit of a sequence, so you are going to define the sum of a series in terms of this limit of the partial sums. So how are you going to define? Just think logically. So suppose you are going to, if you look at the sum of the series, it is same as looking at the limit of SKs, right? Because SKs are actually the series only. Okay, so as k goes to infinity, actually you are going to get the series only. So basically, instead of finding the limit sum directly, you are going to look at the sequence sk and going to take their limit. So if the series is convergent, or if the series has a fixed or finite sum, what is the meaning of that? It means this sequence of partial sums, it should have a fixed or finite limit, which is called this S, which is the sum of the series. So this is how we are going to define a convergent series. Suppose the sequence of partial sums does not have a limit. Suppose you are getting infinity, or suppose you are getting differing values, then we will say that the sequence is not convergent, or we will say that the sequence is divergent. So that is the idea here. Okay, so these are some examples I have already told you. So this is the SKs here. Okay, so also we will write this as limit. So suppose the sequence is convergent, we will write it as limit k tends to infinity sk is equal to s, where s is said to be the sum of the series. So this is the idea. Okay, now we will discuss some familiar series, and we will do some problems based on this familiar series. So the first familiar series will be our geometric series. Already you have studied geometric series in your lower classes, so we'll just keep carrying out the concepts. So what's a geometric series? It's a series of the form a plus ar square plus AR cube plus etc. So there are many notations are there, you can use any notations. So this is a geometric series, and the result is that this series will converge if modulus of R is less than 1 and diverge if modulus of R is greater than or equal to 1. So it's very important, this condition. This series will converge, so this series will have a finite fixed sum if modulus of R is less than 1, and it will be divergent if modulus of R is greater than or equal to 1, and the sum is actually A by 1 minus R. The sum is actually A by 1 minus R. So the type of questions which will be coming is that they will give you a series. You have to identify which type of series it is. If it is a geometric series, you can check for convergence by just looking at whether your modulus of R is less than 1. Okay, and from that you can say whether the series is convergent or not, and if it is convergent, you can always find the sum, which is A by 1 minus R. So this is the idea which we are going to implement in this session here. Okay, let us try to see one example here. Okay, so this is it here. So this, remember this condition, it will be divergent even if modulus R is equal to 1. So be careful here, it is greater or equal to 1. Okay, now let us see one example here. Let us look at this example, 5 by 4 raised to k. Okay, sigma k is equal to 0 to infinity 5 by 4 raised to k. Okay, so whenever you are getting a problem, if you can't identify the series at first, just try to write first few terms of the series. Okay, so can you write the series, first few terms of the series? It will be 5 by 4 raised to 0, which is 1, plus 5 by 4 plus 5 by 4 square plus etc. Okay, so we can see that this is actually a geometric series with A is equal to 5, and what's the common ratio which is going to increase here? It is actually 1 by 4. So your R is 1 by 4. So you can say that your modulus R, which is modulus of 1 by 4, is less than 1. Therefore this series is convergent. It's very easy. Therefore this series is convergent. And now can you give me the sum of the series? It is nothing but A by 1 minus R. In this case A is actually 5, 1 minus R is actually 1 by 4. So it is 4 minus 1. So it is actually 20 by 3. Okay, so please correct me if I am wrong. So I hope it is clear. Okay, so we will do one more problem, simple problem. Let us look at this series now. So I don't know whether it's a geometric series or not. So we'll try to write few terms here. So what will I do? So it will be simply be sigma k is equal to 1 to infinity 3 raised to 2k, 5 raised to 1 minus k. So when k is 1, you will be getting it as 3 square. Okay, 3 square into 5 raised to 1 minus 1, which is 0, plus next one, when k is 2, we will be getting it as 3 raised to 4, okay, plus 5 raised to 1 minus 2, which is minus 1, so I will be getting it as 5. Okay, again 3 raised to 6 by 5 raised to 3 minus k, again 5 square, okay, plus etc. Now can you identify, so can you see that some term is being multiplied here? So we can see here that a term of 3 square by 5 is being multiplied, right? 3 square by 5 is being multiplied here. Okay, so here there was 3 square by 5. So again you add 3 square by 5. So this is your R. Okay, so this is your series, this is your R. Now tell me, is the series convergent? Now your R is actually 9 by 5, which is greater than 1. Therefore this is not convergent, it is divergent. Okay, so there is no need to find sum now. I hope it is clear. So just write first few terms. I try to identify which term it is. We'll encounter many type of series here. So just try, for every problem, try to write a few terms. Okay, and then try to identify the pattern of the terms. So that is what you are going to use it. Okay, so we will do some more problems here, some basic other problems also. So now let us look at this problem. Find the rational number represented by the repeating decimal 0.784, 0.784, 0.784. So this question is not as infinite series per se, but you can bring in infinite series. Okay, actually can you write this decimal as an infinite series? Can you write this decimal as a summation of an infinite number of terms? Can you write this decimal as the summation of an infinite number of terms? So if you look at this, you can see that this 784 has been repeating, right? So it will simply be, if you observe closely, it will be 0.784 plus 0.000784, right? Plus 0.00000784. Okay, plus this is my series. I am writing, expressing this decimal as an infinite series. Or in other words, for your for your convenience, I'll write it as 784 by 10 cube, right? This is actually 784 by, what is it, 10 raised to 6 because 6 terms are inside, plus 784 by 10 raised to 9 plus etc. Now, can you observe that what type of series this is? This is a geometric series, and what is the common ratio? The common ratio is 1 by 10 cube, right? Because 1 by 10 cube is being multiplied everywhere. Okay, and the first term was actually 784 by 10 cube. Okay, don't forget that 784 by 10 cube. So this is your A. Now how will you find the sum? So basically 1 by 10 cube is R, which is less than 1. Therefore, this series is convergent. So how will you find the sum? It will actually be A by 1 minus 1 by 10 cube. Okay, so it is actually 1000. So basically this will be 784 by this 10 cube and 10 cube will cancel out here, and the denominator will be 10 cube minus 1, which is nothing but 999. So this is the rational number represented by this quantity. Okay, I hope it is clear. Okay, so this is the steps here, you can check it out and try to do this homework also. So here you have to make a slight tweak here. So basically this question has 5.232323. Try to do it yourself. So before you use this 5, you may lose the pattern, so you just consider the number 0.23, 0.2, so 0.23, 0.23, 2323, etc. Make it into a rational form, then you add 5 to it. Okay, otherwise you will be getting confused regarding the pattern of the. So basically for this question, okay, so just keep 5 separate for some time, and just go for the rational representation of this one, and then you add 5 to it. Okay, I hope it is clear. Okay, so moving forward, now let us look at this problem. Find the value of x for which the series converges, and find the sum of the series for those values of x. So here actually they are asking you the condition for which x is, or the interval in which the value x is, or the values of x for which this series converges. So they are asking you the values of x for which this series converges. If you look at this series, you can you observe that this is all, since we are already discussing geometric series, obviously it will be geometric series only, but can you observe that this is a geometric series? So which term is being multiplied here? So here I am multiplying 3 by minus x by 2. Here it is x square by 4, or again I am multiplying it by minus x by 2 square. Okay, again minus x by 2 cube. So basically I am multiplying this series by minus x by 2 only. So minus x by 2 is my common ratio. R is minus x by 2. So this series will converge if mod R is less than 1. So if mod minus x by 2 is less than 1, or if mod x by 2 is less than 1, or this series will converge if mod x is less than 2. Okay, so this series will converge if mod x is less than 2. And if mod x is less than 2, can you find the sum? Okay, it's also very easy. It is nothing but a by 1 minus r. A here is actually 3. 3 by 1 minus, your r is minus x by 2, minus x by 2. So it will be 2 plus x. Okay, so it will be 2 plus x here. So it will be simply be 2 plus x. So 2 will go to top. So it will be 6 by 2 plus. So this is the sum. Okay, so these are the problems involving geometric series. Okay, so very simple thing. I hope it is clear. Okay, now we will discuss another interesting series called telescoping series. It's a very simple thing, just a simple observation is there. So this is the telescoping series. I'll tell you why, show you why it's called telescoping series. So this series is of this form, 1 by k into k plus 1. It's a standard series. Okay, so this series, the finding or discussing the convergence or divergence of this series comes from a simple observation. This 1 by k into k plus 1 could actually be written as, so as we do in calculus, I can actually split it into 2 like this, k plus 1 minus k, right, by k into k plus 1. Okay, it is actually 1 by k minus 1 by k plus 1. Okay, so k plus 1 minus k into k plus 1. So it is actually 1 by k minus, so this is this term. Okay, so if you make this observation, so I am going to look at the partial sums. So what is my S1 here? S1 contains only one term, so it is actually 1 by 1 into 2, which is actually 1 minus 1 by 2 from here. Okay, what is my S2? S2 is actually 1 by 1 into 2 plus 1 by 2 into 3, which is nothing but 1 minus 1 by 2 plus 1 by 2 minus 1 by 3. How? Because 1 by 1 into 2 can be split like this, and 1 by 2 into 3 can be split like this from this observation. Or it is nothing but 1 minus 1 by 3. Okay, now can you tell me the pattern? What is your S3? S3 will be similarly 1 by 1 into 2, 1 by 2 into 3, 1 by 3 into 4. So it is 1 minus 1 by 2, 1 by 2 minus 1 by 3, 1 by 3 minus 1 by 4. Everything is cancelled out. You will be getting it as 1 minus 1 by 4. So what is your SK? SK will be 1 minus 1 by k plus 1 if you understand this pattern here. Right? Now, what is limit? So I am going to find the sum here. What is limit k tends to infinity SK? What is it? It is nothing but limit 1 minus 1 by k plus 1, and when k tends to infinity, this 1 by k plus 1 will go to 0, or you will get the limit as 1. So basically limit k tends to infinity SK is nothing but limit k tends to infinity 1 minus 1 by k plus 1. If you take the limits, limit k tends to infinity 1 is 1 minus limit k tends to infinity 1 by k plus 1 is nothing but nothing but 0, because this k is in the denominator. So that means Sk has a finite fixed sum, therefore the value of which is nothing but 1. Therefore this series converges and the value is nothing but 1. So this series is called telescoping series. So the basic problem was based upon this observation that 1 by k into k plus 1 could be split into 1 by k minus 1 by k plus 1. Okay, and why it is called as a telescoping series? Very simple thing, because your SK actually depends. So when you suppose this is a telescope, I can actually make it smaller by I can put in these tubes together so that it will become like this, because this will go inside this one, this will go inside this one, and can be compressed. So we can say that when you write SK, the intermediate terms will vanish and only the first and last term would be lying. Okay, just like a telescope. That is why it is called telescoping series, because the intermediate terms would vanish once you split the terms like this. Okay, that is why it is also called as a telescoping series. Just a humorous interpretation, that's it. Okay, and moving forward, one final result for you, which we will be using in the next sessions, not for the sessions, which is called an important series, which is called the harmonic series or the P series, and the proof is not required for you. It's very important series. So this series, the harmonic series, will converge if P is greater than 1 and diverge for P is less than or equal to 1. You can find the sum is difficult. So this is the result. You have to be careful with this. So it's very important. So I will write some common harmonic series. So 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus etc. Very important series. And now can you tell me whether the series converges or not? Okay, so you can see that this is actually a P series with P is equal to, observe what is the value of P here, P is equal to 1, and when P is equal to 1, you know that the series diverges. So this series will diverge. Okay, and suppose I am looking at this series, 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square. It is not a geometric series, be careful, it is not a geometric series, it is again a harmonic series with P. What's the value of P? Observe both of them, the P value is 2, where P is greater than 1, therefore the series converges because P is 2. Okay, and tell me again, suppose I am looking at 1 plus 1 by 2 raised to maybe 3 by 4, okay, plus 1 by 3 raised to 3 by 4, plus 1 by 4 raised to 3 by 4. Now tell me whether the series converges or diverges. Your P value is actually 3 by 4, and what is 3 by 4? It is actually less than 1, therefore this series also diverges. Okay, so this observation should be made. So only this result is required for you. From that you will be, so basically this harmonic series are used to find the convergence or divergence of other series using some tests. We'll study some few tests in the next session. So for those tests you should know the theory of this, you should know the idea of this harmonic series. For those tests you will be using some comparison tests there. Okay, so for those comparison tests this is required. That is why I'm just introducing this harmonic series. So remember, the harmonic series converges for P greater than 1 and diverges for P less than or equal to 1. Okay, so look at this one here. Can you tell me whether this series converges or not? So if you can identify this is a P series, your P is actually 1 by 3. Okay, so can you say the series diverges? Okay, so these are some other examples here. Please go through these examples also. So here can you see that? So if you look at the series, it is not obvious that this is a harmonic series, but if you look closely, it is one, because it's actually 1 raised to 1 minus 2 by 3 plus 2 raised to minus 2 by 3 plus 3 raised to minus 2 by 3. Just write few terms. Okay, it will be like this, or it will be simply be 1 plus 1 by 2 raised to 2 by 3 plus 1 by 3 raised to 2 by 3. Here look at the series. So what's the p-value here? P-value is 2 by 3, which is less than 1. Therefore this diverges. So we can check out these examples also. So that is very simple. So harmonic series is very, very important. Only this result is required for you. We will be using these applications in comparison test in the next session. Okay, thank you.